Hello everybody and welcome to CS202 video 6. I hope you all are having a good Wednesday. So today we are going to be talking more about pointers and dynamic memory allocation, which is one big usage of pointers. So let us begin then. Okay. So we got, since we have 6 viewers, we'll see. So let us actually start by doing a quick review on pointers from last class, okay? So pointers are a type of variable, just like integers, doubles, floats, and strings. And they're built in. Pointers are built in. Strings technically are not, by the way, but pointers are built in. And the pointers have to be of a specific type, and that is what they point to. So it could be an integer pointer, could be a double pointer, could be a string pointer, could be a class pointer too, which we'll talk more about in a minute here. There's two major operators that you use when dealing with pointers, and that is the dereferencing operator, which is the asterisk, and then there's the address of operator, which is the ampersand. And so you use both of these operators with pointers to either get the address of a variable and then save it to a pointer, or once you have an address in a pointer, you want to access the contents of that address that your pointer is pointing to with the dereference operator. So the way you do that is, for example, let's say we have a variable x integer stored in an address, and it has a number 25 in it. And then we create a pointer called p that is of integer type, which means it can point to integer variables, okay? And so what we're going to do is we're going to make the pointer point to the location of variable x. We use the address of operator as shown here. And then by doing that, we are finding whatever address x is in, which will vary. Every time you run the program, you're going to get different addresses because that's beyond your control. That's the operating system's job to assign you specific memory locations. In this specific instance, it happened to be at address 100. Now, this is address 100 in hexadecimal. So the way you know it's hexadecimal is because you see the 0x in front of it. And so what you're doing here is you're technically getting the address 100 and storing it in p. P itself is a variable. It's a pointer variable, but it's a variable at the end of the day. So that also needs to be stored in memory somewhere. So p has actually an address too, which is address 200. And what we're doing is in that location, we are storing the address of x. So if you were, by the way, if you were to say cout and then cout just p, you would get address 100 because that's what's in p. But if you say cout ampersand p, so if we replace this here with an ampersand, we'd actually get the address of where p itself lives, because all variables have an address, okay? Everybody lives somewhere. There's no homeless variables here. And if you want to get their address, whether it's a pointer or not, you use the ampersand. It just turns out that pointer variables, instead of storing, floats, integers, or strings, or cars, they store other addresses, okay? And so when you dereference it, what you're saying is go to whatever p is pointing to and get me that data. So that is going to address 100 and getting the 55, okay? So that's basically what we did last time. We also talked about how to initialize a pointer variable. It turns out that it's a good practice to initialize all your variables in C++, right? Because otherwise they could have unknown information in them, which can cause problems. And so whereas you normally initialize like an integer to 0 or 1 or one of those values, or it could be really anything, it just depends on what you're trying to do. It turns out that with pointers, it just makes sense to initialize them to one of two main ways. And one of them is to initialize them to the value of 0, or to use the word null, which actually just initializes it to 0. We do also have a no PTR version of that, but that's only available in C++ 11, so you can use it, but just FYI, otherwise the code won't compile. And so what does it mean to initialize a pointer which is basically holding an address with 0? Address 0, what is that? It's not a special address. I guess it might be actually, but we don't consider it to be special. It's just any other address. So it's not enough to just initialize a pointer variable and sort of be like, oh, this pointer is now safe. No, because if you actually try to access address 0, your program will crash. Now, what does it look like when a program crashes? You get that error that we saw that was called segmentation fault. And so that basically means your program tried to do something that it shouldn't have, and either it was terminated by the operating system because of an error, or because you were accessing things that you shouldn't have accessed, right? And so basically, what has to be done in combination with initializing your pointer variables to null or to 0 is that whenever you're accessing them, so whenever you actually want to dereference a pointer, so whenever you're doing like asterisk PTR essentially, you want to check first if the pointer is pointing to null or basically has 0 in it. And you do that with an if statement like this. And only then, after you do this check, then it's safe to do this. So it's a good practice to always, whenever you are dealing with pointers, to always check if they're not null before. Now, this isn't going to completely solve all your problems. This is only going to solve the problem of a pointer that's not initialized. And vice versa. When you finish using a pointer variable, it's a good idea to set it to null to sort of label it as not in use anymore. That way, you avoid accessing addresses that you shouldn't, or potentially invalid addresses, which I suppose is kind of the same thing. Okay? And this will actually come more into play when we talk about dangling pointers today as well. But I think that was pretty much it. That was pretty much last class. And so we're going to start today by talking about a special case of pointers before we talk about dynamic memory allocation. And that is using pointers in classes. After all, we spent about a month talking about object-oriented programming. So more than likely, you can kind of predict that we will be using pointers with classes, right? And so it turns out that there's a little bit of a trick that you need to know when using them in classes to make your life easy. So let us first start by showing you that a pointer doesn't have to point to integers, doubles, or strings, or built-in data types in general. It can point to anything of any type, including custom data types such as classes or structs. So for the sake of this, let's go ahead and create a struct here called student type, which I'm just going to abbreviate as ST. I can't do the curly brackets. Screw this curly brackets. Okay. So let's just add in a variable in here. We'll say GPA. That's a relatively useful information to keep about a student, right? Of course, there can be more. We might add more, but for now, we're just going to do that. Okay. So in your main, let's say that we want to create an object or instantiate an object of this class. Okay. This is a struct, but whatever, it could be a class. The only reason I made it a struct is because that way I don't have to put the word public. So if you were to do that, all you have to do is put the type name and then a variable, and a valid identifier. So in this case, we'll do S. Okay, that's no news. You've been doing this for the past month or even longer than that. And so, okay, moving on to actually something interesting. Let's make a pointer that can point to an object of student type. Okay. To do that, it looks very similar to making an object, with the only difference being that you're going to put your little asterisk in front of the variable name. So now, whereas this is just a random object, this one is a pointer variable of type S_T, okay, which is student type. Watch out. The watch messes up the tablet, so I always have to take it off. So yeah, okay. So every time or any time that you want to make an object, and then you want to make a pointer point to an object, all you got to do is make a pointer of that type. In this case, of that type of object, of that class. And the way you do that is basically you just put that little asterisk there, and bam, you have created a pointer. Again, in C++, while there is a way around this, and it's really bad, you use reinterpretcast basically, and we'll talk about it at some point, maybe next week. But normally, outside of those really bad scenarios, you want to make your pointers be of the same type that they're going to point to. Okay, that's by design to make your life easy and the compiler's life easy. So don't try to make an integer pointer point to a string or to a student type. Similarly, don't try to make a student type pointer point to an integer or a double. Okay, there's a reason for this that will kind of make more sense as we explore pointers further. especially when we talk about virtuals and up and down casting. But it's just good practice. And frankly, if you try to make an integer pointer point to a double, you're going to get an error pretty much, unless you do it in a specific way with reinterprecast, which you can get around with using f permissive flag, but don't. The fact you're getting an error, unless you know any better, probably means that you shouldn't be doing that in the first place, right? Okay, so anyway, we have a pointer and we have an object. Let's make that pointer point to the object, okay? So that's very simple to do. Here's your pointer, it's called SPTR, and just like we did with the integer before, all we got to do is put the object name, which is that, and then what we're trying to do is make SPTR point there. So we need to know where to point to. We need the address of it. And so we're going to use the address of operator to get the address of S. Bam, ampersand, we're done. So what this is doing is, this is storing the address of S in SPTR. Okay? That's basically what you're doing. Cool. All right. Now I've shown you that you can use this with classes, but here's where it gets a little bit interesting. Okay? So now we have this S that's basically pointing to, or sorry, SPTR that's basically pointing to S, right? So before, if we wanted to access the GPA class member variable in a student type object, how would we do that? Well, we would go ahead and put s.gpa, right? And then maybe we could assign this to like 4.0. You wish. So how do we do that with the pointer? You might be inclined to think that all you have to do is just replace the word S with SPTR and then just use the dot on the GPA. You know, and suppose you wanted to just, you know, they're like, nah, you're not getting that GPA, you're getting 3.5. Okay? So you might be inclined to think that this is enough, but this will not work. The dot member access operator, you know, is going to try to think of this as a regular object, but it's not a regular object, it's a pointer. And so what you need to do is you need to dereference that pointer to tell it, because remember, the pointer is just an address. If you want to get what you're pointing to, you got to dereference it. So you got to add the asterisk. So you would have to add an asterisk here to dereference this address, and then once you basically add S, which is what we're pointing to, then go ahead and put the .gpa. However, this is still not enough, okay? Because it turns out that in C++, you know, you have order of precedence, right? Such as like the multiplication and division operator have higher precedence than the addition and subtraction, right? And that's supposed to mirror the same idea with, because that's how we do it in math, right? Or the parentheses have higher precedence over any of those, right? So there's a certain order of precedence in C++. One of the ones that people aren't too familiar with is that the AND operator has higher precedence than the OR operator, and that's by design, okay? So it turns out that within the member access operator and the dereference operator, the member access operator has higher precedence than the dereference operator. So maybe I should write that down. So the member access operator has, so I forgot to write the word the, higher precedence Dang, it just looked messy. I gotta write slower. Press. I just get impatient writing. Has higher precedence than the reference. By the way, also known as the indirect operator. Okay, so what does this mean? This means that think of like the member access operator, the dot, as being a multiplication symbol, and the asterisk is being an addition symbol. So of course the multiplication is going to happen first, right? And then the addition. And that's not good for us, because what we're trying to do is we're trying to dereference SPTR. You know, we're trying to basically do this first and then do the .gpa part, okay? So that's what we're trying to do, but that's not what we're getting right now. What we're getting right now is we're basically getting the .gpa happening with the SPTR first, and then we're getting the dereference of that, which makes no sense at all, because SPTR GPA, you know, would get us some sort of class variable, which it won't, because SPTR is not even an object, and then it will try to dereference that. Okay, so double bad. So what we need to do is we need to force the program to dereference SPTR first, and then go to the GPA part of that. And how do we do that? Well, how do we change the following operation, which is basically what we have, 4 plus 5 times 6. And right now, we're trying to make it so that the 4 plus 5 happens before the multiplication. How do we do that in math? Okay, dramatic pause, 3, 2, 1, 0. We put parentheses, right? And now we do the math, that we do the addition first. And so that's the same thing we're going to do here. We just need to go ahead and put in parentheses. So big spiel just to tell you that parentheses fix the problem. But if I just told you without explaining the why, you probably forget it. And you might still, but you know, at least there's less chance of you forgetting it. So this basically says dereference SPTR, which takes us to S, and then we do s.gpa, which takes us to the GPA class variable and stores 3.5. So this will store 3. You know, that's kind of bad. Let's do 3.9. Let's not ruin their hopes and dreams. Store 3.9 in s.gpa. Okay? So that's very important to know. Anytime that you're dealing with pointers, you know, you have to understand that the dot operator, the member access operator, has higher precedence than the asterisk. Okay? Let's switch it around. Let's go ahead and add a pointer in here. So let's say that in addition to being a GPA, may we have a string pointer to a name. Okay? Now, technically we have to make that point to a valid name. Okay? We haven't done that, but let's just say that we had that in there. Here's the thing. If we have such a thing in there, how do we access it? Well, we could do s.name. However, we need to dereference name, right? How do we dereference name? Like, we need to put the asterisk, right? So, can we do this? Not quite, because that's not how the member access operator works. However, what you really need to do is you need to go to s.name and then dereference that location. So really what you're trying to do is dereference both parts of it, like that, okay? And if you do that, you might be inclined to say, well, what we're trying to do is this. So we want to make sure you have the parentheses. But no, we don't actually need the parentheses in that scenario because of the order of precedence, you know? It's like trying to say 4.5 times 6 again, but this time we want to guarantee this happens, so we put the parentheses. To which I return and say that's unnecessary because it's going to happen first anyways because of order of precedence, right? So it turns out that in this scenario, we don't even need the parentheses. You could have them, you know, if you want to look like an amateur coder, you could have them, and then people would look at you like, wow, this guy doesn't know order of precedence. But, you know, you don't need them, right? And so essentially, if you do that, now you can go ahead and actually store a string in it. So let's make a string here on main called n and just assign John Wick to it. And so now if we want to assign the name there, we can use our ampersand, which is your address operator, and then n. I don't know why I picked John Wick. I recorded a lecture yesterday for 301 and I kept using the word John Wick. I don't know. I haven't seen the movie recently, but just kind of segue into this class. So, okay. So as you can see, this is sort of the opposite situation of the one above. In the case that what you have is a class member variable that's a pointer, you need to dereference that to be able to access it. And the way you do that is with the dereference operator, which you can just put at the beginning like that. And understand that because of the member access operator, this is happening first, and then this is happening. Okay. So that's the other side of the coin. Okay, so anyways, let me, before I give you the happy solution, let me show you what's going to end up happening here, okay? So let's switch over to the IDE. What says, nodal updates can be installed. I don't want to install updates. Linux. Okay, so let us very quickly write what I had in there. So just to prove to you that it doesn't make a difference, this time we're going to call it a class instead of a struct. now we have to put the word public. So we have double GPA, and then we had string name. Okay. So what we're gonna do is the same thing that we did here. We're gonna create a object, and we're gonna create a pointer. Then we are going to drink water because I'm thirsty. So stand by. Okay, next we're going to go ahead and I guess make a string called name or just n, and then put John Wick in it. John Wick. And what else did we do? Well, that's it. Then we're gonna make it point to each other. Okay, so we're gonna get SPTR and we're gonna make that be pointing to S like such, and then we are going to prove to you that it's working by assigning the GPA first to 4. And then assigning it, or yeah, how about we just see out it, or yeah, let's see out it first, just to show you like before and after. And then let's change it with by using SPTR. So SPTR dot GPA gets 3.9, and then let's go ahead and see out it again, so you can see that it was changed. And then let's go ahead and put in name into S. So S name is going to get the name, which is N. And that's what we have so far. So last thing we'll do, I guess, is we can see out it. Okay. And to do still is how will we see out it with SPTR. Okay, but first let's just see if everything compiles and runs. It did not. SPTR %s. Oh, I forgot the asterisk. That's why. Here we go. And then S name %n. Why doesn't it like the name string there? String S% string n equal John Wick. It's trying to convert it to a C string. Invalid conversion from string to car. Oh, I see why. I see. Because technically speaking here, I am accessing the location of the pointer and I'm trying to update the name, which is not what I want to do yet. I just want to make it point to name. So there I want to do that. But then if I want to change John Wick's name, you know, then I will do that. So typo there. What's John Wick's middle name? I don't know. John Wick. We'll just call him John Wick 2. Okay? So I guess before that, let's see out it just to show you. So s.name. No, not SPTR, S. Okay? So yes. So, all right. So let's go ahead and analyze each line of code and make sure that everything was working. So this first 4 is coming out from line 16 right here. And so as we can see, we stored GPA 4 and then we print it out. No surprise there. But then we actually go ahead and make a pointer that we have here and use the pointer to access the GPA using the dereference operator and the parentheses because of the order of precedence. And we change it to 3.9. We go ahead and see out the GPA again with the S. As we can see, it was changed. But never in the code did we do s.gpa get 3.9. We did it through SPTR. So that's the cool part about pointers. You know, you're doing it with this alias, SPTR. Okay? Then next we went ahead and did this line of code. So this is where I had the little typo earlier. So what we're doing is we are updating the pointer. So this is getting us the pointer and updating that pointer with the address of n. Okay, you don't need the dereference operator here because all we're doing is we're updating the pointer. We're not updating what the pointer is pointing to, just the pointer itself. We can then see out what that pointer is now pointing to with the dereference operator here, which is why you see the asterisk here, because here we're counting what the pointer is pointing to, which is of course John Wick. From there, we want to change what the pointer is pointing to, that contents of what it's pointing to. We want to change those contents. We don't want to change the address. We still want it to point to n, but we want to change what's in n. We could have done it by saying n equals, but instead we're going to use the pointer to do that. So we do that by saying as name and then dereference that and then change it to John Wick 2. Then we can see that it indeed was changed. If I went ahead also and see out at this point n, you would see that this also has now John Wick 2 because n and name are both the same thing because name is just pointing to n. So there's only one string in this whole program so far, and it's just n. The name is just pointing to that n. That's it. Okay, cool. So last thing, let's use our pointer SPTR to access the name. Okay, so this is kind of like mix matching. Okay, because what we want to do is we want to basically, let's just see out it. Let's say we want to see out the name using SPTR. How do we do that? Okay, we can't just do this because that's just not going to work, right? This is a pointer and then this is also a pointer. So we have two pointers basically here. Okay, so how do we do it? Well, we know that for the SPTR part, we can do this, right? But then order of precedence breaks this, so we got to put it in parentheses. So that takes care of the SPTR part. However, if we see out this like it is now, all we're going to get is an address. This address is actually the address of n, but we got to dereference that address to get to the name, the actual, well, to whatever name is pointing to, which is n. So to do that, the contents of it. So to do that, we have to dereference the outside, like that. And that one does not need a parentheses around the whole thing, so you don't need these parentheses like this. I mean, I'll put them out for now, but you don't need them because of order of precedence. It's like trying to put parentheses around the multiplication part when it's totally unnecessary. Okay, so as you can see, that will indeed print John Wick, but if I get rid of them, it'll also print John Wick. So as you can see, the parentheses are absolutely unnecessary, and it actually looks bad if you put them. Okay, so this is a little bit weird, you know. We went from not using pointers to using like what looks almost like an emoji here. Okay, so let's look at this a little bit closer to make sure that we understand it again. This dereferencing is, first of all, we have two asterisks because in this case we have two pointers. Okay, we have a pointer for SPTR and name. They're both pointers. This one we dereference directly here, and we put the parentheses around it so that the dot does not, you know, supersede it, and that gets us the location of the class. Okay, so the SPTR is getting us S essentially, which is the name of the actual object. That's getting us a location of S. Now S has a bunch of variables in it. In this case, two of them. We got to get to the right variable. To be able to find that location, we use the member access operator, which is a dot, and the name. Think of that like a little +2, you know, +1 and +2 to get there. So 1 and 2. So that is going to get us to the right location of name. Now, name is just a pointer. So we need to dereference that to get to whatever name is pointing to, which is the location of our actual name. That's where the second asterisk comes in. And there you go. Okay? So hopefully you know, you caught it one of those two times, but we're going to do a lot of examples of this. So you'll get it as we go. All right, so already though you should be like, oh, this is annoying, why are we doing pointers, right? Well, let me tell you, there are a lot of usages of pointers that are very, very good, but even before we go any further, let me make your life easier by showing you another way of doing at least something as nasty as this. In fact, actually, before I show you, let me scare you. That's probably better. So we already talked about inheritance and aggregation. So suppose that we wanted to go ahead and keep another student type object inside this class. Okay? So, of course, if we just try to do something like this, this will not compile because this is like a infinitely recursive thing. Well, you don't know recursion yet, but it's infinitely creating objects because like we're saying there's a class and inside of it there's another class. So to be able to create the class, we got to figure out what's inside of this class. So we look in there. Well, this has another class in it, and inside another one, and another one, another one. It goes forever. It's like a little matryoshka doll that never finishes. Okay, so that's one of the reasons why we can't do that. We can't make we can't make an object of the same type as the class that's in. However, with pointers, we can do that. We can just make it a pointer. So we're saying we are going to have an object, we're going to point to it, but we don't have to. And that will mean that the matryoshka doll will basically end at some point. Okay? So that's kind of cool. I guess that's one of the good things about pointers. But the whole reason of this, to show you and scare you, is let's go ahead and say and see how would we access S2's GPA, for example. Okay? So right now, S2 is just null, you know, or actually it's not even null, it's just uninitialized, right? So if we wanted to access it, you know, if we're accessing with S, we can do like S and then S2, right? But that's a pointer. So let's go ahead and assign that pointer to S. Okay, now what does this mean? Well, this is like a circular definition because we have a student pointing to themselves, essentially. Okay, it's like me pointing to my own back. That's okay. It's just for a point. We could have made another student and have a point and be like, this is the student's best friend or something, or like collaborator. But in this case, we're just saying it's pointing to yourself, okay? So suppose that we wanted to access the GPA of S2, okay? So we would do s.s2.gpa. However, S2 is a pointer, right? Actually, we need an ampersand here because this is an address of S, but yeah. So suppose that we want to access this GPA. The thing is that this is a pointer. So we need to put an asterisk to dereference that part. So where do we put the asterisk? Does it go there? No. Does it go there? Yes, it does. But yet again, you are going to need the parentheses because you need to make sure that this piece gets the reference first before you do the GPA part. So now if we were to and see out this, we would find that it actually has, I think, what, 3.9, because it's a circular reference. You call it a circular reference when you're pointing to yourself. So there you go. Okay. But if we were pointing to another student in here, then it would point to other student's GPA. Okay. Cool. Let's do the same line of code using SPTR instead of S. So in that case, SPTR S2 GPA. Okay. So first we gotta dereference the SPTR part, so we do the asterisk, but we need to put the parentheses because of order of precedence. That takes care of that. Now we gotta do the S2 part, which is what we did above already, which means we gotta put another parenthesis here and here because of order of precedence, and in between we gotta put in the dereference operator, like that. Are you scared yet? If not, then we can keep going. But as you can see, that does indeed work. I hope you're seeing a pattern here of how these are being set up. But now, let's go further than that. Because inside of S2 is another S, we could technically access the GPA of the student's collaborator. So let's go ahead and do that one. And let's just skip and go straight for the hardcore one, which is the SPTR one. So to do that, we would go ahead and do SPTR.S2.S2 again .GPA. That would be the student inside of the student, so the student's collaborator. Students, I'm making sure I'm seeing the right number of students. The student's collaborator, yes, yeah. So I am saying the right number of students, okay? Here's the first student, this is the second student here. So okay, so now let's go ahead and put in all the parentheses and all the asterisks. So first let's go from the left to the right. So that takes care of the first pointer. Then we gotta do the second pointer. And finally, we got to do the third pointer because of order of precedence. And do that. And hey, what if we actually wanted to modify the GPA at this point instead of just outing it? In fact, what if we wanted at this point to see out not the GPA, but the name? Yeah, the name's a pointer too. That one doesn't need a set of parentheses. You just got to put in the asterisk here and you're good to go. But yeah, so that one should see out John Wick, as you can see. I guess put in an end line so it looks prettier, but yeah. Okay? So as you can see, whenever you have a pointer, whenever you have an object that has a pointer inside of it, which is another object, and that could keep going forever, this can get pretty complicated to keep track of here, okay? So the C++ developers, the C++ gods, as we would call them, looked down upon this and said, hey, this is actually kind of nasty. And it can only get nastier the more nested it becomes. And so they said, let us make their life easy for once. Not always, but this one time. And so the arrow operator was born. So what is the arrow operator? In C++, the member access operator is actually called the dot member access operator. And it's because we also have now the arrow operator. The arrow operator, first of all, it's made up of two symbols. The sort of the less than sign, well, the subtraction sign, and then sort of like the, well, I guess if you're looking at it, it could be greater than or less than, I don't know what you call it, but it's that one, okay? That one right there. So you just put them together, no space in between them, and you create the arrow operator, okay? So the arrow operator is very, very, very useful because it allows you to dereference pointers without having to use all that nasty parentheses and asterisk stuff. It basically solves the problem of order of precedence with dereferencing and the member access operator. So whereas before we had the following line of code here, well, I'll just rewrite it. In the basic one, at least. Before we had this line of code, well, we needed the parentheses, right? Make that period bigger so it's more noticeable. With the arrow operator, this will simply become SPTR arrow GPA. That's it. And the other example that we had, I had something of the type of to make sure I copied that right. It's a lot easier to type code than it is to handwrite it. So yeah, I got it right. So this mess of a code would very simply become SPTR S2 GPA. It's like a little harp, like that's kind of like to make it seem like it's cool because it's really nice. Okay, you don't have to worry about figuring out where to put the parentheses and whatnot. Lastly, the last one we did where we had the S2 and S2 inside would also just become SPTR2 S2 S2 GPA, or I guess that one was name. The name one, however, because name is a pointer, then we do have to put a one asterisk over here. Okay. So we have first question. Does that automatically dereference whichever pointer it is after? It will dereference the one before, not after, because technically speaking, this arrow part is dereferencing this part, okay? And then this arrow is dereferencing this part. Actually, I like a color like that better. And then this, oh, there's no more arrows there. For example, this arrow here is dereferencing this part, okay? So that's what it's doing. The name part, however, does not get dereferenced. This name is not being dereferenced. That has to be dereferenced with this guy because name happens to be a pointer. Whereas GPA is not a pointer. It's just a regular variable. It's a double, okay? So yes, I hope that answers the question. So I have it here as the TLDR version of this, so I will write the TLDR version of all this, which I hope you guys know what that means. Too long, didn't read. When you want to access members of a structure, use the dot operator. When you want to access members of a structure through a pointer, that's the different part, use the arrow operator. Okay? So the full name is the member access arrow operator, actually, versus the member access dot operator. But I think some people call it the dot member access operator and the arrow member access operator. Doesn't matter, whatever. But yeah, that's pretty much what I have about that. Yeah, so let's go ahead and do that in code. Can we use it instead of the member access operator? Both are member access operators. It's just different ways of accessing members of that. So they're interchangeable, yes. If you can write code with the member access operator, you could probably write the same code with the arrow, as long as you're dealing with pointers. If you're not dealing with pointers, could you do it still? Ooh, that's a good question. I've never done that. But I think you could if you used the address of operator. That might be a good thing to try, actually. Never tried it before. So like if I want to change, if I want to do this using an arrow operator, I think you can. You just have to use the address of operator. I don't know why you ever want to, but you know, if it's a question, it's good to know the answer to it. However, I suspect that in this case, we will need to put parentheses around that one. Let's see if that one works. I'll feel happy about that. Like, wow, okay, that's cool. I've never done that in my life, so at least that I would recall. However, here, let's make sure, because I don't think that would work without the parentheses. But let's see if it would. Nah, it wouldn't work. Okay, cool. So basically, it's like the inverse of the other one. So I suppose, yeah. Then my statement will stand that anything you write with the dot operator, you could rewrite with the arrow operator, and vice versa, as we've discovered today. What would the compiler say if we did that without the address of operator? It would say basically the error that you got. There's no pointer type, or vice versa. So suppose that we did, so you're saying if I used, for example, instead of doing cout sptr GPA, you're saying what would the compiler say if I didn't use that? Well, if you used the other method with the asterisk and the parentheses, you'd be okay. It would compile just fine. But if you do this, it's either going to segmentation fault or it's going to complain and say that it's a pointer. In this case, it says it's a pointer. So there you go. Request from member GPA and SPTR, which is a pointer type. Maybe, oh yeah, that's right. And it always does, the compiler is pretty cool about that. It always says like, hey, maybe you meant to use the arrow operator, which in this case is true. So it's not wrong. I see my stream is delayed considerably. Oh, if you have a delay in the stream, you can always try to refresh. That will sometimes help a little bit. But yeah, it's unfortunate. It just kind of happens. I set it to low latency mode. It's supposed to be like 3-second delay, but I have seen cases where it's like 30 seconds. That's why sometimes I just do those dramatic pauses when I ask questions, because I know the delay is going to be like forever. So yeah, but yeah, try to refresh. Might help. So anyways, let's do this one with the arrow operator. So that would be SPTR S2, and the autocomplete even like appears with the stop, which is a good sign. You know, in fact, here let's just go crazy and do like 50 of these, because why not? You know, and then finally at the end of this, because it's all basically circular right now. Cout name. Now we do need to put here, because if we just do this, we're just gonna get an address right now. Oh, I forgot. There we go. Last one. I didn't put an arrow on that one. And right now, here's the address, right? So if we don't want the address, if we want the contents of the address, we dereference those. And then we're going to get, of course, John Wick. There you go. Can't get rid of him. So yeah, that's the arrow operator. It's supposed to make your life easy, so use it. However, be aware and understand how it works without it. Not because you want to, I mean, like, there's no logical reason as to why you'd want to do this, like, other than to make your code unreadable, which is never a good thing. However, while you won't do it because you know better, others might not. And so there might be some crazy person that's using this method instead of the arrow operator. So you should understand how it works so that if you happen to run into such bad code, which you probably will at some point, you know what that code means. And then you can even refactor and make it better using the arrow operator, right? But if not, at least you can read it and understand it. So if you're debugging code and you see this line of code, you can understand it and see if there's an error in it, okay? So it's not to say like, hey, okay, I'm going to use the arrow operator, I'm just going to forget this even existed. No. Because while you might not use it, coding in the real world is about collaborating with people, which can mean great things, but it can also mean bad things, such as dealing with bad code already out there. So you should know it, so that if you run into bad code, you know how to read it, okay? So don't just totally disregard this, understand it. And what does that translate to? Then I'll ask about it in the test as well. So you should know it, okay? But silver lining being, don't ever use it yourself. Just be aware for whenever others use it. Okay, so that's how you use pointers in classes, essentially. Moving on. Okay, so you've seen an example of why pointers could be good, I suppose, because of what I was doing here. We're having an object of student instead of student. Like, that's actually a very good usage of pointers that we would not be able to do otherwise. It would not compile. It would tell us errors. Definition of class T is not complete until the closing bracket. See that? So that's why you basically can't put an object of student type instead of another one, because it just infinitely creates themselves. Case in point, right there, right? And so that's one good usage, I suppose. Another good usage is sometimes it's actually useful to have a way of having aliasing, which is what we're doing here. It's having two things that point to the same location. It can also be bad because if you change one of them, you are technically changing the other one because it's the same thing, right? So it might be easier to miss when you're doing a change like that. And then you're like, whoa, when did this change? But the main use of pointers as to the why they're really, really, really important is what I'm going to talk about next. And that is for dynamic memory allocation, which is, of course, one of the topics of the day. So, what is dynamic memory allocation? Okay? To understand that, let's break it down and talk about what dynamic even means and what a dynamic variable would be. Okay? So normally, when you create a program, you're writing code until now, exception of vectors being the exception, I suppose, you, at compile time, tell in the program the exact size of all of your data structures. Okay? So if you have an array in your program, you know exactly the size at compile time. That way, when the program starts up in memory, it knows exactly how much space to allocate for your program. It can tell the operating system, this person wants to use 100 slots per se. Okay? There's 100 variables or whatever. That's it. It's never going to be 101. It's never going to be 99. You may just use partially that space, but the point is that you're always going to reserve the same amount. Okay? That is called static variables, essentially. Static variables or static memory allocation. Static memory allocation is better because static variables you might confuse with actually static variables. So yeah, static memory allocation. Okay? On the other hand, so let me write that actually. Static memory allocation. On the other hand, there are scenarios where it is beneficial to not have a fixed size that is decided at compile time. Typically for efficiency purposes. Suppose that you had a program that sometimes needs 10 slots, other times needs 100, and sometimes, few but some, it needs 1,000. If you were limited by static memory allocation, you would want to be safe and say, okay, I'm always going to reserve 1,000 just because of those edge cases that actually require 1,000. Okay? If you try to do 100, your program's going to break when it try to do 1,000. So if you want to be extra safe, you have to make it 1,000. You have no choice. With dynamic memory allocation, you basically say, I don't know how much memory I'm going to need until I actually need it. And that is good because that means you're only going to request what you're actually going to use. You're not going to request more, and of course you're not going to request less because you need it, right? And so to do that, you have to use special operators in C++ that are called new and delete. And so those are going to allow you to, at runtime, declare variables and allocate variables is a better term, allocate variables or allocate memory to use it. And better yet, you could do it in the middle of your program. It doesn't have to be at the beginning. And in the middle of your program, while you're still working, you can release that memory, allocate more, release, and basically kind of like a use on demand system where if you need something, you'll take it, and then when you're done, you'll give it back, hopefully. Okay? So how is this actually handled in memory? Let's kind of jump into CS219 for a minute here. CS219 being where you're really going to talk about this in detail along with 370. I think the other day I was talking about memory. Well, I drew pictures, right, of different addresses and so on, right? You got an address 100 and then address 200 down here and so on, right? Well, let's go a little bit further than that and understand how memory is actually sort of split. It turns out that static memory allocation gets stored in what is known as the stack. On the other hand, dynamic memory allocation gets stored on what is known as the heap. Okay? So they're completely different locations in memory. The heap is on demand when you need it at middle of runtime. The stack is fixed, and that's where your program actually gets loaded when it starts up, and it gets decided how much space you need based on what you wrote in your code. So how can we have two completely different types of memory in just one stick of RAM? Because let's say we can't afford 2 sticks of RAM, okay? And even if we did, it wouldn't be good if we did it the way I'm going to first show you. One way you could do it is you could just split it in half. If you have 2 sticks of RAM, of course, you could say one's going to be for the stack and one's going to be for the heap, right? And let's say these are both like 4 gigabytes of RAM. You could do that. Or let's say you have 1 stick of RAM, you could just evenly split it, right? You can split it right down the middle and say the top is going to be for the stack, the bottom is going to be for the heap. It's 8 gigs of RAM because it's just 1 stick, and we're just going to fill it up starting from here, right? And starting from here. It'll work. This will work just fine. But what's the downside to this? The downside to this is that when you're doing your programs, nobody tells you or forces you to say that you have to use either either static or dynamic memory. You can mix and match as you want. For example, sometimes you might always need to have an array of a fixed size. So you go ahead and you declare an array with the old school method, static array, right? But maybe you also need to have a dynamic one. So you have both. That's okay. You can have a piece of both, right? And then all your static stuff is going to be all here, and all your dynamic stuff is going to be all here, right? Here's the issue. Suppose that you have a program that requires 5 gigabytes of RAM. You have 8. You're like, no problem. I got 3 to spare. Easy. Well, guess what? It turns out that the 5 gigs of RAM that it needs are like 4.9 of that are heap stuff because they're dynamically allocated. And 0.1 of that is stack stuff because it's statically allocated. Turns out that the stick of RAM you have with 8 gigs of RAM is not going to be enough for this. You're actually going to run out of space because you can only fit 4 here. And that 0.9 can't fit it anywhere. You can fit the 0.1 here. You got all this empty space that you're not using, but you can't. You can't use it because it's a different type. So you can see how splitting it down the middle is not the most efficient way because you are going to run into a situation where basically you have the space, but you can't use it. Okay? So, what did the people, smart people that develop memory and stuff, thought about? Well, let's go ahead and use a stack data structure, which you will learn about near the end of the semester, which basically is like filling things up from one end and up like this or like this, like a stack of plates at a buffet. You know, you put them in. That's actually the example I usually give nowadays. So again, we'll talk about that later. But for now, what we're gonna do is we are gonna start filling the stack from the top and the heap from the bottom. But what we're gonna do is we're gonna just keep throwing it in like this. Fill it up this way. In fact, here, let me use the colors for that. You're gonna fill it up this way over here, and then the stack you're gonna fill it up this way. Okay, but here's the thing. You don't have a boundary between them. What does that mean? That means that if you're not using the stack fully, or sorry, if you're not using the heap fully, but using the stack a lot, you could have something that's like really, really big on the stack and very little on the heap. You could also have something that is very big on the heap, but very little on the stack. No problem. You could have something that is like pretty much entirely heap and no stack at all. Like, well, there's always going to be a little bit, so I'll just put it like that. Okay, and vice versa. The beauty of this system is that, you know, they grow and shrink as needed, right? And so you could have a program that is like very stack heavy or very heap heavy, and it's still going to be okay. Now your program that requires 4.9 gigs of heap and 0.1 of stack would actually look like this. Assuming that it's an 8 gigabyte stick of RAM, then it's going to be like that much for the stack, and then for the heap it's going to be about half plus change, so like that, and there's still a big gap, right? There you go. Problem solved. Problem solved until you run into problems, that is. Because what happens if it turns out that you really need a program that requires like 9 gigabits of RAM, okay? You have 5.3 gigabits of stack, gigabytes, not bits, and then you need like 3.7 failed. No, that's right. That actually equals to 9. Okay. Of heap. Well, typically what ends up happening is, again, the stack stuff you know at compile time. So it means when you start running it, you're going to pre-reserve that. So there we go. The heap, on the other hand, is stuff that you kind of allocate on the way. So you might start with nothing here, but we're saying it's going to grow up to this size, right? And so you're growing, you're good, everything is fine, it's growing, it's getting to 3, it's going beyond 3, bam! You are overwriting over your stacked stuff. Or the vice versa, if you were, well, no, vice versa is never going to happen. It's always going to be the heap overwriting the stack. Otherwise, the program would have started. This is bad, because you're overwriting your own information. It's like two pieces are like killing each other, essentially, okay? This is what is known as what the famous website is, Stack Overflow. And it's a really, really bad thing that you will not want to happen, okay? So a Stack Overflow is when you run out of space and you're basically smashing your stack, also known as stack smashing, I suppose. I believe that's another nickname for it, stack smashing. So, kind of bad, right? Because overriding over your own stuff, not a good idea. It's like stepping on your own tail kind of thing. If you were a dog, I suppose. So, could they do that? I'm assuming they can. I was thinking of my dog, if I've ever seen her do that. So, yeah, that's a bad thing, right? But anyways, that's my little 219 aside about how memory works. So when I'm talking about dynamic memory allocation, and you will see, because I will go ahead and see out the address of a dynamic variable, they're typically very, very, very different locations in memory than the heap ones. So like you saw an example of a variable that was in the stack over here. You can see the numbers here, right? When we come back in a minute and do dynamic stuff, you'll see that the address is very, very different. And that's because it's pretty much in a completely different location in memory, right? Although this stuff is all virtual versus physical addressing, so you gotta take all this with a grain of salt. Weird that it's called stack overflow, since the heap is overflowing in the stack, not the other way around. Stack match makes more sense. Maybe that, yeah, I know, I agree with you. But I was thinking, because I'm trying to think if there's a scenario where the stack would overflow. You know, I suppose you could if you have talking about the call stack with function calls like recursion, and then there it would make sense that the stack is actually destroying the heap. You know, so maybe that's maybe more, that one makes more sense then. But again, they're pretty much interchangeable. Like either one is bad. It basically means that the stack and heap are touching. It doesn't matter who did the initial touching. When they're touching, bad things happen. So yeah. But yeah, interesting. So either one of the terms I'll go with. So anyways, dynamic variables, okay? So those dynamic variables, you know, let me go ahead and put a little nice definition for those, which again, they're basically variables that you make on the fly. But the official definition is variables that are created during runtime. Or better said, program execution. Okay, and how do we make these variables? You might ask yourself. Well, I have an answer for you. And the answer is with the help of pointers. Like pointers, yay! Yes, with the help of pointers, C++ creates these variables. Dynamic variables. Okay? So, how do we do it? It's not just pointers alone. They need a little extra help, and that's what the new and delete operators are. So, to create and to destroy, that is the question. Which shall we talk about first? Well, I think it's better to create something before we destroy it. So, let's go ahead and talk about new first. I know this, but I don't want to spoil it. Of course, I know. Yeah, there's the dramatic reveal, right? So, new and delete are reserved C++ words, by the way. So just like if, include, public, private, what else? Using, I suppose. Else, for, while. Yeah. Pretty much anything that like highlights in a different color when you're coding. So yeah. So anyways, the way that you create a dynamically allocated variable is you are going to use the keyword new, and then you're going to put the data type of the variable that you're trying to make. Okay, so that's the syntax. That will allocate a single variable. Okay. So allocate single variable. If you want to make an array of these, which might be very convenient, you can do it pretty easily too. You can use the same new data type and then some sort of expression here that indicates how big you want that array to be. Okay? So I'll give you some actual examples of this in just a second. One-dimensional array, by the way. So let us go ahead and try using the new operator. Let's just actually do it directly on the computer. Actually, how about before I show you that, let me show you the delete so then we can just hop over. So to do the delete, it's very simple too. You put the delete keyword and then you put in the variable name. Okay? What does delete do? Delete is a little bit misleading actually, because delete does not quote unquote delete a variable. Deleting, when we think of delete, we think of like erasing from existence. That's not really what happens. When you delete a variable in C++, or when you're using the delete keyword on a variable in C++, better yet, you are de-allocating that variable. Okay, so delete var name is going to delete a single dynamic variable. What does that mean? When you allocate a variable, you're saying, operating system, Linux, Windows, Mac, yo, I want this data type variable. So why does the operating system need to know the data type? Because different data types require different size. Very simple example, an integer might require 4 bytes. A double may require 8 bytes. So it matters how much space you need, because the operating system needs to know how much to give you, right? If you're doing a class variable, that's going to be a lot bigger because there might be like 2 integers inside. Like our student type has a double and a string, right? The string's a pointer, so it's smaller. It's just an address basically, but it's still an address which needs to be stored, right? It's probably going to be 4 bytes, and then the double, and it has a double GPA which is 8 bytes. It's probably going to be a total of 12 bytes. So it matters. Okay, so new data type is really telling the operating system, I need a variable of this data type, so go figure out how big it is and give it to me of that size. Okay. De-allocate, on the other hand, is like, hey, operating system, thank you so much for giving me this variable. I don't need it anymore. Please take it back and feed it and give it to whoever else needs it, because I don't need it anymore. You know, you're that friendly neighbor. You know, you give it back after they loan you the space. Okay, that's what de-allocation does. It's just giving it back. As we will discover next class when we talk about memory leaks and dangling pointers, de-allocating is not deletion. De-allocating just gives back the memory, but it's still existing there, and the contents are probably still valid, which means you might still be able to access them, but that's going to cause some risk associated to that. Okay, so yes, that's delete for you. Okay, if you want to de-allocate an entire array like the one we just did over here with the data type here, you can do that by using the same sort of syntax, delete, and then your variable name. But in between, you're going to put, and this is kind of weird, square brackets like that. This is not a typo. This is how you do it. You put delete space, the square brackets with nothing inside, and then the variable name. I think you got to put a space as well. I don't know if you need a space. You might need a space here. I usually just put a space. And that will, again, not the word delete again, that's misleading. De-allocate a dynamic created array. De-allocate a dynamically created array. Okay, so let me go ahead and show you examples of that. And I will upload these examples today since it's Wednesday. Okay, so let us start by making a pointer. Actually, here, no, let us naively do this. New int. Bam, I just allocated a brand new dynamically allocated array. I'm going to go ahead and run it to show you that it compiles. Furthermore, I will talk more about background next time, but it's something that's going to be very, very important for you to understand. We're going to use background for it here, because background is going to tell me if I'm currently using memory. Why is this ./a.out? There we go. I can see here, it says leak, but whatever, that I have created 4 bytes. Okay, if I was to comment this line out, I would see the same, and then compile and run again. I see 0 bytes out. So I guess that's my only proof to you so far that I have created memory, or I have allocated memory. However, good luck trying to use that here. Like, how do I actually use this variable I created? Well, here's the problem. This new operator will tell the operating system, hey, I need a variable I need a memory location for an integer. The operating system is going to come back to you and say, okay, this is the address. And so new is returning to me an address. But if I don't store that address anywhere, I've lost that address. I might as well never have asked for it. In fact, if I do something like cout new int, you can see that because you will see that that actually just returns to me an address. And by the way, look at this address. This address is very, very different than, I can't scroll up anymore, than the one from the other program that was much bigger. If you rewind the video, you'll see that the other address is much, much bigger. Why? This is heap variable, so it's a very different location than memory. It's going to be different every single time, but it's very, very different than the other ones, which are much bigger and have like a bunch of F's and 7s and whatnot. So, okay, I created a memory, a dynamically allocated variable, but I'm just kind of creating it and throwing it away. How do I store it? How do I store it so I can access it later? And that is where pointers come into play. Remember, what can pointers do? They can store addresses, right? So if I am creating an address from this, why not just store that address in a pointer? Like such. So now I'm saying, create a pointer, done. In fact, here, let's split it into two lines because it's the first time you ever see this. So create a pointer, done. Second thing, allocate a new dynamically allocated variable, and then store that address in PTR. Okay, great. So now I can see out the address, but better yet, I can dereference that address and store a number. And then let's go ahead and print it out. And if we do that, we will find that now we are able to use this dynamically allocated variable. That's great. Great, great news, right? We can run Valgrind again to see that indeed we are using memory. However, let's say that we're done using this memory. Right now, we're just kind of keeping it. And then when the program ends, when your program terminates, any memory that you've allocated that you're still holding on to, will be automatically returned when your program terminates. Okay? It's like the program dies, and then it's like, well, he doesn't need this memory anymore, so I'm going to reclaim it. However, in the middle of your program, you're able to return that memory early on. Why would you do that? Because you're a good neighbor. You don't need this variable anymore. Why hold on to it? Give it back to the computer so other games or other programs can hog on memory and use it, right? So in this case, we're going to use the delete operator to deallocate it. So we need to pass in the variable name, which in this case is a pointer, PTR. This says, hey, I'm done with PTR, so please go ahead and take it back. As you can see now, it says 0 there. This Valgrind tells you how much memory you held onto at the end of the program and you hadn't given back before. And we consider that to be a memory leak. We will talk more about that on Monday next week, so to be continued on that side. But ultimately, you always want to return your memory, especially if it's like in the middle of your program, because otherwise, you know, you're holding on to it whenever you might not really need it. So, yeah. What else do I want to say? Oh, I guess very quickly, last minute, let's make another example with an array instead of a single pointer. Okay? So let's actually use the PTR. So PTR, let's say that we want to make an array. The syntax again is new. The data type, which again, let's make a double. Oh, no, let's make it an integer because it's an integer pointer. And make it size of 5. Of course, now this could be a variable in here. You know, this could be a variable that you read into CN or something. So it's, because otherwise it's static. So why do it in the heap in the first place, right? So you want this typically to be some sort of expression or variable. And then to delete it, you would do the delete square brackets and then PTR like that. In between, just to show you, let's go ahead and store something in it. So like PTR2 gets 22. Then let's see out it. And this should hopefully see out 22. You can see it here, 22. I of course show you the output of Valgrind. The Valgrind does show you the output, but like that you can see there is the case. Okay? I know, so it is not definitely lost technically, right? Yeah, so memory is, when we say it's lost, we're just saying we don't have access to it. But when your program ends, it does get returned. It doesn't just disappear forever. Like, it's not like your piece of memory just burns up if you don't deallocate it. It's just held onto until the program terminates and then returned. But even if your program was to crash in the middle, whatever happens, when your program ends, it will return the memory. Like, it will be taken back, essentially. Okay, the operating system remembers what you gave, what it gave to you, and when it sees that you stop working, or you crash, or you terminate normally, it will reclaim that memory. Okay, that's why, again, it's skipping ahead into memory leaks, which again we'll talk in detail more about next time. But that is why some video games that have memory leaks, as you might hear the term, they just tell you, hey, if you just restart your game once in a while, so that it kind of fixes that. And that's because those memory leaks that get allocated or get built upon with time can be then kind of cleaned up if you close the program, because the operating system will take the memory back, and then you run it again, and now you kind of start allocating more memory leaks. Okay, so yes, they're not like lost forever. You don't even need to restart the computer. You just have to restart the program. So yes, that is where I will end it. Next time we will talk about memory leaks, dangling pointers, and practicing allocating dynamically allocated arrays, but more than just like a single dimension. So we will definitely do more practice of this, because we will need this for assignment 4. Okay, so assignment 4 will be published on Saturday, and it will be due for quite a while, so because we still have to finish talking about this, but you can probably get started on it anyways. I recommend you do, actually. So yeah, any last minute questions? Pointers, big topic, so that's why we're taking our time with it. I want to make sure that everybody's following along with it. All right then, I presume that there's no questions, or there's an extremely massive delay. So in that case, I know it's Wednesday, but I won't see you until next Monday. So I do wish you to have not just an amazing day, but also an amazing weekend, and to get some rest, stay safe, and, you know, everything going well. I shall see you again on Monday. So you're welcome. My pleasure. See you guys. And any questions, Discord, email, Canvas, whatever you want, I am available. So see you all later.